So everything that we talk about is joint work with Dario Cordero from Paris. And let me start by reminding you a little bit about Brunn-Minkowski inequalities. So I fix some measure mu on Rn, and I call rho the density. And I want to know when this measure satisfies a Brunn-Minkowski type inequality. I mean an inequality that looks like this. The measure of a convex combination of two sets, and those are any Borel sets, should be at least the average of the measures of A and B. And the average, you can take any kind of average you want, right? Kappa equal 1 is arithmetic mean, kappa equal -1 is harmonic mean, kappa equal 0, I interpret in the limiting sense, could be geometric mean, and so on and so on. So as kappa becomes bigger, those inequalities become stronger, of course. And I want to know when does the measure mu satisfy this kind of an inequality. And there is a result that I will call the Borel-Brascamp-Lieb theorem, even though you can argue a little bit about references, that gives you a very clean, very simple if and only if condition for when this is true. You look at the density rho. I assume my measure has a density. It's not so important, but let's assume this. I assume the measure has a density rho, and then I need rho itself to have some kind of a concavity assumption. And here there is some power alpha, and here there is some power kappa, and there is some relationship between this kappa and alpha. 1 over kappa is 1 over alpha. Okay, so in particular, if I want to look at the biggest possible kappa, the biggest possible kappa is 1 over n, then this alpha must be infinite, which means that the density must satisfy this condition. By the way, you do see my mouse when I move it, right? My cursor. Yeah, thank you. So it must satisfy this condition, and of course, this just means that rho is constant on whatever convex support is. So, right, the corollary of this Borel-Brascamp-Lieb is that if I have a measure, and this measure I wanted to satisfy Brunn-Minkowski with the optimal constant, with constant 1 over n, you can, with exponent 1 over n, you cannot do any better. And I want this for all Borel sets and all lambda between 0 and 1. The only possible such measures are uniform measures on convex. There are no other examples. If I take, for example, another measure, right, an important measure to take is the Gaussian, I will always denote by gamma the standard Gaussian on Rn. It has this density, E2 minus Euclidean norm x squared over 2. If I look at this measure, then it's very easy to check, right? It's just an exercise in calculus, that it satisfies our assumption, but only with alpha equals 0. You cannot take alpha to be bigger than 0. This is a log-concave function. Its logarithm is concave, which means that we get this inequality where, again, on the right-hand side, we have a geometric mean, but we cannot do any better in general. But there is a surprising result, a fairly recent result of Ashkenazis and Motzidis, and I will give more references a little bit later. Let me, postpone it for 5 minutes. That says that if the sets I take are not any Borel set, but they are convex and importantly origin symmetric, so k is equal to minus k, l is equal to minus l, then in fact the Gaussian measure satisfies a Brunn-Minkowski inequality with the optimal constant, the optimal exponent 1 over. So this is some kind of magic that is facilitated by the origin symmetry of the convex part. And this didn't come out of nowhere. It was a conjecture of Gardner-Zvavitch. Okay, in their paper they said, well, maybe it's true even without symmetry, maybe it's true even if both K and L contain the origin. But there is a counterexample of Liran Rotem that says that this is impossible. So the question was, is it true for origin symmetric set? And yes, this is. So, okay, for the Gaussian it's true, but this of course raises the obvious question, for which measures is true? So I want to know for which Borel measures on Rn it's true that they satisfy the Brunn-Minkowski inequality with the optimal exponent 1 over n when the sets you plug in are convex symmetric. This is the question. This is the main question for now. all the main results and questions will be in these boxes. So if you get bored, you can just read the boxes and ignore everything else. So this is the question. Let me say a little bit about what was known about this question, and the answer is not a lot. So I will call this conjecture, I will call this inequality DBM for dimensional Brunn-Minkowski. But it's Brunn-Minkowski where the exponent is exactly 1 over the dimension. So this obviously holds for uniform measures of convex sets. We just said it, even without the convexity assumption. And we just said it holds for Gaussians. Okay. Now, conditionally, if you believe the log Brunn-Minkowski conjecture, which I will not define, it's not so important to us, but it's a standard conjecture in convexity, and which is, I think, widely believed. And if you believe it, it follows that every even Borel measure, which is log-concave, satisfies this inequality. This is a result of a Lifshitz-Marsiglietti, Liran-Zvavitch. And I defined what log-concave means, right? It's just the case alpha equals 0 here when I have the geometric mean on the right-hand side. But, you know, first of all, this is only a conditional statement because we don't know log Brunn-Minkowski. And even if we knew it, this would not be an if and only if. This would be a sufficient condition, but not necessary. So even this will not completely answer the question, but it gives some examples. In particular, in dimension 2, we know log Brunn-Minkowski by the works of Borotsky, Luttwak, Young, and Zhang, so we also know that all log-concave even measures in dimension 2 satisfy this. And essentially, I think those are the only examples that were known. Basically, we know Gaussian, we know dimension 2, we know uniform on convex sets, and that. Now, if you are willing to write here instead of 1 over n, a worse exponent, essentially 1 over n to the 4, it was proved by Lifshitz that this is true in every dimension, for even log-concave measures. Okay. So what is our result in this direction? We have more results, but let's start with this. So I'm going to define a certain class of measures. So I fix, from now on, I will have the measure mu, and I will always denote the density of mu by E2 minus double. It's a bit more convenient to have the function on the exponent. And I want to talk about a very specific class of measures. So a measure mu has property star if it's rotation invariant. And when I look at this one-dimensional function, it is non-decreasing and it has some kind of convexity property. Not that W itself is convex, but the W of e to the t is convex. This is weaker. And I don't have a good name for this class, so I will just call it property star, just for this talk. I don't have a very good name for this class of measures. And the theorem that we proved is that every measure with this property satisfies this dimensional Brunn-Minkowski inequality. So some examples, right? So for example, obviously, if I can take E2 minus Euclidean norm to the power P over P or not, it doesn't matter. P equal 2 is the Gaussian, this was known. P equal infinity is uniform measure on a ball, this was known. But all other P's were not known, and now we know them. And maybe an even more interesting example, we do not assume the measure is log-concave, right? This condition is weaker. So you can take these Cauchy type measures, right? These measures that have polynomial decay. They also satisfy our condition. So they also satisfy dimensional Brunn-Minkowski, which actually was a big surprise for us because we talked a moment ago, right? I will go up for a moment about this Borel hierarchy of concave measures. And these measures are not in this hierarchy, right? If I take these parameters, alpha and beta here to be small enough, then these measures don't satisfy even the weakest possible Borel-Brunn-Minkowski inequality if I plug in general Borel set. So it's a bit surprising that if you plug in convex symmetric set, all of a sudden you get the optimal result, the optimal exit. But this is true, so this is our result. This is our geometric result. I promised you in the title of this talk, spectral inequalities. So I want to talk a little bit about how this geometric result follows from a Poincaré type inequality. Of course, if there are any questions, feel free to stop. So here is the Poincaré type inequality improved. So we take a measure mu, again, density to minus W with the same conditions as before, right? In particular, I will remind you that W of X is small w of the norm of X, it's rotation invariant. And I can take mu itself, or I can take any measure which is even and more log-concave than mu. So there is a question of Emmanuel in the chat about, is it important here that the measure is finite? And well, I need it to be, I guess, locally finite, because otherwise everything is infinity maybe, if there's some singularity at 0 or something. But I don't think it's important that the measure is finite. We have some examples of measures with integrable singularities. I don't think it's important that the measure itself is finite. But let me go back. So we took our measure mu, and now we take a measure mu, which is log-concave with respect to mu. So its density, the density of mu times another log-concave function. And then we can prove this Poincaré inequality. We take a function h, which must be odd. This is a technicality, but an important one. So it's centered in any reasonable sense. And then the integral of h squared with this weight is bounded by the L2 norm of the grade. So here are a couple of examples, right? The examples from before. If I take this measure UP from before, we get this nice inequality. And in particular, if P is 2, if we have the Gaussian, we get the standard Gaussian Poincaré inequality. And of course, this Gaussian Poincaré inequality, this one, we know this is true not just for odd functions, for all centers. But in particular, this is a special case of our theorem in the odd case. For those Cauchy measures, I took here power 2 just to make it look a bit nicer. You can take any alpha, it doesn't matter. This is the inequality you get. And both of these, all of these inequalities are sharp. If you plug in linear functions, you get equality, and mu equal mu. So those are sharp Poincaré inequality. And I want to talk a little bit, this is pretty quickly, about what is the relationship between this spectral inequality and our geometric result. And as it says here, most of the argument is known, exactly what happened in the Gaussian. So this will be my chance to give you some references about the Gaussian case and to explain what's really going on. So remember, we want to show that this Brunn-Minkowski inequality with exponent 1 over n. So it basically means that we want to show that this function is a function of lambda is concave. This is what this says. So how do you check that something is concave? You differentiate twice and you check that the derivative is negative. And because of some technicality, if I know it for every KNN, it's enough to check that the second derivative is zero. You don't have to check it at any other point. You can think about this, it's not so important. So then you compute the second derivative, and it's a little bit messy, but you can do it. And in this case, here is the formula you get. This is what it means to check that the second derivative is negative. Now, I know this is messy. You don't have to really read it. It's not really important. I'm not even going to explain what is this h and what is this 2. It's not really important. And where did this function f come from? It's not important for us right now. What's important is that this thing is some inequality that looks kind of like a Poincaré inequality, but on the boundary of the convex body. And okay, so I took this formula from a paper of Kolesnikov and Lifshitz that I will explain in a moment. The actual computations of the derivatives are taken from a paper of Kolesnikov and Millman, which I will also explain in a moment. But this is the formula you take. And now the question is, how do you prove this? And the trick, and this trick is originally from this paper of Kolesnikov and Millman, is that I don't want to work on the boundary of K, I want to work on the interior of K. So I take this function f, this function here that I didn't explain to you where it came from, and I solve some kind of a strange PDE on the body K. So I look for a function u on the body K, such that L of u, this is the operator L, is equal to 1, and u has f as the Neumann boundary condition on the boundary. And then I take this inequality and I try to write it in terms of u instead of in terms of f. And I will not show you how it's done. Of course, you have to use some differential geometry formulas and Cauchy-Schwarz somewhere, so you lose something in the way. But eventually, you get this state. So again, for our problem, this was done by Kolesnikov and Lifshitz. For the LP Brunn-Minkowski, this was done before by Kolesnikov and Millman, but in any case, this is what you get. So in order to prove our result, the inequality you really have to prove is this one. This is the infinitesimal form of our inequality. You have to prove that for every symmetric body K, and for every even function u with L of u equal 1, you have this inequality, where this is, you take the Hessian, it's a matrix, you take the Hilbert-Schmidt norm. And if you prove this with constant 1 over n, you get what you wanted. If you prove this with constant 7 over n, you get Brunn-Minkowski, but with 7 over n. Whatever you prove here, you get. And then Kolesnikov and Lifshitz used this theorem, and they were able to actually show this with C equal 2, which was almost optimal. And then, like I told you, Ashkenazis and Mutsidis were able to improve C equal 2 to C equal 1 and for the Gaussian case, and then they proved the result for the Gaussian. Now, originally, when this talk was supposed to be 35 minutes, I planned to show you this proof, this Ashkenazis Mutsidis proof. It's very short, it's half a page. But now in 25 minutes, I don't have time, so you will believe me, you can open it, it's nice. But the point is that this is a very short proof, and basically the only place where you use the fact that you are working with the Gaussian is when you use the Gaussian Poincaré inequality. This one, the one I wrote here, this one. So it turns out that if you take the proof and you change very little, you basically do exactly the same. But instead of using the Gaussian Poincaré inequality, you use our weighted inequality, you prove exactly the result. So basically, our Poincaré inequality, this theorem, implies the geometric theorem, basically using the known Gaussian. This is not very, very new. Okay, I have like 5 minutes. Late. Let me tell you another result. So here is another geometric question. So I will say that a measure mu has the B property if it satisfies this inequality, this Brunn-Minkowski type inequality, for all origin symmetric convex body space. Now, this is not comparable in any way to the inequalities we talked about before, right? Because on the one hand, it's more restrictive because I only take bodies that are homothetic. But on the other hand, here, I took something that is much smaller than the average of those sets. I took here some kind of a geometric average. So this is another type of concavity, which is not comparable to the previous ones. And again, you can ask which Borel measures have this property. And again, what is known? So this holds for the Gaussian. This was Cordero, Fradelisi, and Poincaré, answering a question of Banaszek that was published by Rafa Latawa. Again, if you knew log Brunn-Minkowski, you could do some things. And in this case, there is one more example. So there's a very nice paper of Ashkenazis, Nayar, and Koch that uses this result for the Gaussian to prove the result for certain Gaussian mixtures, which I don't want to explain what it is. So again, you can probably guess our result. So our result, every measure with this property star, those rotation invariant measures we talked about, has the B problem. Satisfy this inequality. And again, you have to check the proof infinitesimally. You have to check this inequality infinitesimally. Unlike the previous case, the case of the dimensional Brunn-Minkowski, here we don't have Kolesnikov and Lifshitz to do the work for us. So we have to, invent the infinitesimal form ourselves. So we invent it, and here it is. This is a Brascamp-Lieb type inequality. What does it say? So I assume that I have a measure mu that satisfies this property, and again, mu is log-concave with respect to mu, even the usual assumptions. I normalize mu to be probability measure just for simplicity. And then the statement is that for every even function, we have this Brascamp-Lieb type inequality. Without this term, you probably know this. This is the Brascamp-Lieb inequality, not the one that Karoli talked about yesterday. Yesterday, Karoli said there are two Brascamp-Lieb inequalities. This is the other one. So without this part, this is well known, and you don't need F to be even. But the whole trick is that you need to add this part to make the inequality strong. So again, you can write down some nice examples, right? Those are the two examples from before. For this measure, e to the minus x to the p over p, you can get such an inequality that bound the variant by this weighted gradient with this constant, one. And for the Cauchy measure, for this measure, you again get a very nice Poincaré inequality. And both of them are sharp, at least in the sense that this constant is optimal. There are equality. I think I have like 2 minutes. So let me just say that, first of all, this theorem follows from the Poincaré inequality I talked about before, using fairly standard L2 argument. You have to be a little bit careful, but again, this is not very, very new. And this theorem implies this geometric theorem, again, in a fairly standard way, once you invent it. It's not so easy to invent this term, but once you invent it, it's not hard to check that this implies this. The most original part of this work, the thing that is the least similar to known results, is the question of how do you even prove this Poincaré inequality. And for this, I really don't have time. I just wrote here a few sentences. You basically do it by using polar coordinates, by using a one-dimensional integration by parts, and then by using some kind of a spherical Poincaré inequality on the sphere that is really the infinitesimal form of the Borel-Brascamp-Lieb we started with. So we started with this inequality at the beginning, this Brunn-Minkowski type thing. You differentiate this, you get some inequality of the sphere that you can deduce from a work of Kolesnikov and Millman, the one I talked about a moment ago. And then you somehow combine all these, ingredients, and some magic happen, and you are able to prove this result. But I don't think I have time to say anymore. So I think I will stop here. Thank you.
Thank you.